Oh yeah, 12. Right. This is quantum physics. This is the one of the last topics for us to do this year. And it's actually part of the waves topic, but it's kind of like a standalone topic, really. It's quantum physics. And this is where it gets really exciting. So I'm going to start by running through a few slides. So this guy here, he's widely regarded as being the godfather of quantum theory or the godfather of quantum physics. Anybody know who he is? Okay. Uh, he is Max Planck. Okay, he's a German guy, lived in the 1800s, died in 1947, so he had quite a long life. Anyway, he's widely regarded as being the godfather of quantum theory. He's the first person to come up with the idea that at a subatomic level or an atomic level, energy is quantized. Now, what does the word quantized mean? Well, the word quanta or quantum, which is singular. Quantum just means a singular discrete packet of something or amount of something. All right. And in this case, energy. So essentially, at the subatomic or the atomic level, energy only comes in discrete amounts or discrete separate packets. So here we go. Let's get started. First thing, photons and the equation E equals hf. So what is this word photon? Okay, you might have a pretty good idea, but this goes back even further. This goes back to a question which scientists have been trying to get to the bottom of for centuries. Okay, this argument raged almost 400 years ago. Okay, and many different scientists had very different opinions. Okay, so is light a wave or is it a particle? This guy, Christian Huygens, a Dutch guy, 1600s. Um, he was. You should know from when you did waves. He's the guy the first explained diffraction. Okay, so he's very much in the wave team. He definitely thought light was a wave. Light was a nice continuous wave. What sort of evidence do we have, or what sort of evidence did he have at the time? Well, you've seen this before. Light is refracted, but diffraction and especially diffraction patterns are very much evidence for light being a wave. Okay, right about the same time as Christian was Isaac Newton, who was actually on the other side. Isaac Newton firmly believed that light were particles. Okay, light was not a continuous wave, but light was actually particles, and he didn't call them photons; he called them corpuscles. Okay, but he said that he did a lot of work on light, but he very very firmly believed they were particles. Okay, well the answer is kind of both. They're both right. All right. This is why quantum physics is really really interesting, because when you get down to the atomic and subatomic level, things are not black and white. They're not right and wrong. There's a lot of grey area. That's what makes it fascinating. So what are photons? Well, one thing photons are not is a continuous wave. So if we were to draw a continuous wave, it could look like that, couldn't it? Okay. Photons definitely have wave-like properties, though. This is where you have to kind of think in the middle. All right. Photons definitely have wave-like properties, otherwise light would not behave like a wave. But they also have particle-like properties. Now, quite a good way of thinking of it is, instead of light being a continuous wave like that, light is like a burst of a wave. They're like little wave pulses. Okay, little self-contained, discrete wave pulses. So they still have a wavelength, they still have a frequency, they still move at a certain speed, just like waves do. But the energy in that wave is not spread out along a long wave. that energy is discrete. Okay? Now that, in a nutshell, is what photons are. Okay? Photons are discrete packets of wave energy, or discrete packets of electromagnetic wave energy. Okay? Now we have different types of photons for different colors of light, don't we? Okay. Let's draw some blue photons. Okay. So they're discrete packets like that. Let's draw some red photons. Okay. So they're discrete, separate. Okay. But they have energy. Each one has energy, but they also have a wavelength and a frequency. Now, the wavelength of red light and the wavelength of blue light, which one has the longest wavelength, do you think? Okay. It's red light, isn't it? We all know red light has a longer wavelength. The wavelength of red light is about, I think it's about 680 nanometers, but blue light is shorter. But we can draw this. If these discrete particles have a wavelength, then they're like particles, but they're like little waves inside a particle, aren't they? Okay. But they're separate, they're completely separate. How would the blue photons vary? Well, they'd have a shorter wavelength, wouldn't they? Okay. So they've still got wave-like properties. They've still got a wavelength, they've still got a frequency. Okay. But they're discrete, separate packets of energy. Now, here's the big question. Which one has the most energy? Like I said, it all comes back to energy being quantized, energy being discrete. Now, which one of these, is it the blue photon or the red photon? Which one has the highest amount of energy? Okay. You'd be right in thinking it's the blue photons. Now, there is an equation. This is the photon equation, which could support that. And it is photon energy equals Planck constant, named after Max Planck, multiplied by the frequency of the wave inside the photon. And the letter equation, so E equals HF, a very important equation. You're going to be seeing a lot of this equation in the next few lessons. Okay, but we've got firstly some units to think of. So what's the standard unit of energy? It is, of course, the joule. What's the standard unit of frequency? It is, of course, the hertz. Okay. Now, what about this Planck constant? Let's have a think about what the value is first. Okay. So Planck constant is 6.626 times 10 to the power of, wait for it, minus 34. It's tiny. The Planck constant is a tiny number. Now, the reason why it's a tiny number is the energy in a photon is very, very small. In a single individual photon is very, very small. Okay? But when you have a beam of light coming from a torch or from a laser, you are talking about trillions and trillions of individual photons, trillions and trillions of individual packets of energy. Okay? So that's why Planck constant is so small. Any ideas about the units, though? Any ideas about the units? Right, let's have a think about this. So if E is HF, then H is going to be E over F, so it's going to be joules per hertz. However, frequency is the reciprocal of time, so it actually becomes joule seconds. Okay? So the unit of Planck constant is the joule second. So let's just write it in there. Okay, so there you go. Planck constant, 6.626 times 10 to the minus 34 joule seconds. The photon equation, a very important equation. Okay. Finally, if we have this equation, obviously energy has to be in joules, frequency has to be in hertz, Planck constant is in joule seconds. Now there's a problem with energy at the atomic and subatomic level, and that is joules are just too big. They're really, really not convenient to use. So we come up with and we use a different unit of energy. Now that unit of energy is called the electron volt, abbreviated lowercase e, capital V. And here it is. Right. 1 electron volt is the energy lost or gained by a single electron when it passes through a potential difference of 1 volt. Let me explain. Here we have a circuit. It's got a cell and a resistor. Now say the cell, the EMF of the cell was 1 volt. Okay? Now each single electron that goes around that circuit, when it goes through the battery or through the cell, it will gain some energy. When it goes through the resistor, it will lose some energy. So gaining energy, losing energy. Now if the voltage is 1 volt, then each electron is going to gain 1 electron volt when it goes through the cell and lose 1 electron volt when it passes through the resistor. Okay, so there you have it. That's the definition of the electron volt. What about these batteries or these cells? Okay, this cell here is 1.5 volts. The EMF of that is 1.5 volts. We remember those from our internal resistance practical. That means that each electron, when it passes through that cell, is going to gain 1.5 electron volts. This one is 9 volts. Each electron that passes through this battery will gain 9 electron volts. So that's what the electron volt is. It's a much, much, much more convenient unit of energy. Okay, and finally, how do we convert? Right. If you remember the equation for voltage, voltage is work done per unit of charge. Rearrange that, we've got work done is charge times voltage. Right. If our work done was 1 electron volt, okay? If our work done was 1 electron volt, so 1 electron volt would be equal to the charge of 1 electron, which is 1.6 times 10 to the minus 19 coulombs. And if it's passing through a voltage of 1 volt, then that's going to be 1. And that is the amount of joules. Okay, so when 1 electron passes through a potential difference of 1 volt, the energy is 1 electron volt. So there you have it. There is our very, very important conversion factor. Okay? 1 electron volt is equivalent to 1.6 times 10 to the minus 19 joules. So hopefully there you can see that 1 electron volt is a small amount of energy. It's a tiny amount of joules. Okay? Well, one of your tasks today is to have a go at these. Just have a quick go at some conversion factors. Thank you very much. See you in